Now we're going to look at Chapter 11, Section 3, Combinations. Objectives. Distinguish between permutation and combination problems. Solve problems involving combinations using the combinations formula. We already talked about permutations, so now we're going to compare that with combinations. A combination of items occurs when the items are selected from the same group and no item is used more than once, and the order of items makes no difference. So this is very similar to permutations, except for the last part. In permutations, the order makes a difference. In combinations, it does not. Combination problems involve situations in which the order of items makes no difference. Example 1. Distinguishing between permutations and combinations. Determine which involve permutations and which involve combinations. 6 students are running for student government: president, vice president, and treasurer. The student with the greatest number of votes becomes the president. The second highest vote getter becomes vice president, and the student who gets the third largest number of votes will be treasurer. How many different outcomes are possible? Solution. The order matters in this particular example because the number of the 3 highest votes determine the office. Here's another one. 6 people are on the board of supervisors for your neighborhood park. A 3-person committee is needed to study the possibility of expanding the park. How many different committees could be formed from the 6 people? Solution. For this problem, the order in which the 3 people are selected doesn't matter because they're all doing the same thing. They're all just on the committee. So this would be a combination. Comparing combinations and permutations. Given the letters A, B, C, D, we can compare how many permutations and how many combinations are possible if we chose 3 letters at a time. The first column contains only one combination, ABC. The second column contains only one combination, ABD. The third column, only ACD, and the fourth column, only BCD. So the letters are in different orders, but we're still picking the same 3 letters from ABCD. We have a formula for combinations. The number of possible combinations if R items are taken from N items is N factorial over N minus R factorial, R factorial. So this is a little different from the permutations formula in that the denominator includes R factorial. Example 2, using the formula for combinations. How many 3-person committees could be formed from 8 people? So we are selecting 3 people, R is 3 from 8 people, N is 8. Putting this into our combination formula, we have 8 factorial in the numerator. We have 8 minus 3 factorial, 3 factorial in the denominator. The top is 8 factorial. The bottom becomes 5 factorial, 3 factorial, because we work in parentheses first. And for the top, the numerator, we can write it as 8 times 7 times 6 times 5 factorial. For the bottom, we have 5 factorial. We're going to write the 3 factorial as 3 times 2 times 1. The 2 5 factorials cancel out. You could also cancel some other things like the 3 and the 2 in the denominator into the 6 in the numerator, and you get 56. Example 3, using the formula for combinations and the fundamental accounting principle. In December 2011, the U.S. Senate consisted of 51 Democrats, 47 Republicans, and 2 independents. How many distinct 5-person committees could be formed if each committee must have 3 Democrats and 2 Republicans? For the solution, the order in which the members are selected doesn't matter, so this is a problem of combinations. At the bottom of the slide, we see what happens if we pick 3 Democrats out of a possible 51. N is 51 and R is 3. So using our combination formula, we end up with 2,825. Continuing this, we have to select 2 Republicans out of 47. So the N is 47, R is 2, and we end up with 1,081. Then, using the fundamental counting principle to find the number of committees that can be formed, we find the product of the 2 combinations, which gives us 22,511,825. And that concludes this lesson.